So to start with, we will start with Oliver Fenwick from Queen's Mary University in the UK. Welcome. And he will discuss or explain us kind of things on thermal properties, organic and hybrid materials.
You're given a difficult job because there's a typo on the program. So I'm Ollie Fenwick, and I'm from Queen Mary University of London. So I'm going to split this talk into three main parts. So we've looked at some hybrid materials, and by hybrid here I'm not meaning composites, I'm meaning halide perovskites, so hybrid organic and inorganic materials. I'll talk a bit about our work on polymers and exploring how the lattice thermal conductivity is not very constant in polymers, and particularly PPHT. And then talk a bit about a question we had at the end of the last, on the talks in the last session, which is about the effects of topography and quantifying the effects of topography on thermal conductivity measurements of thin films. So, halide perovskites. So, I think a lot of you have heard about these materials before. If you haven't, they are materials that are made up of a metal halide cage structure with these octahedra, and you have an entity, often a molecule, held in that structure, an organic cation. They're very processable, they're very good absorbers, they make really great solar cells, solution processable, and so on. Things that we like in organic electronics, but in a crystalline material. And I don't want to say much about this. They're wonderful solar cell materials. My point of showing you this plot, which everyone does show when they're talking about halide perovskites, is to say that the properties we want for thermoelectric material are not at all the same as the properties we want from a solar cell. So why are we interested in them for thermoelectrics? One is they have decent charge mobility. Not record-breaking compared to many inorganic semiconductors, but good, tens to hundreds of centimeters squared per volt second. We want that in thermoelectric materials. Another slightly surprising one, a curious property of these materials, is they have exceptionally low thermal conductivity. So if you look at these graphs here, at room temperature on the right-hand side of the plots, you've got thermal conductivities which are in the region of about 0.5 watts per meter Kelvin. So this is a material with good charge mobility and intrinsically poor thermal conductivity. And that is really tempting from a thermoelectric perspective. So in this hybrid game, I'm trying to capitalize on the quite high, or at least moderate, mobility in these materials and high crystallinity, but also take from the organic side the sort of processability and low thermal conductivity and try and get the best of both worlds. And this is one example which I think shows you why it's difficult to get the best of both worlds in general and particularly in these materials. So we worked with methylammonium lead bromide. So here our metal halide cage is made from lead and bromine, and we've got a methylammonium cation that sort of rattles around in the middle. We synthesize single crystals by an inverse temperature crystallization method, and in that process we introduce bismuth into the structure. Why bismuth? We're just playing a sort of doping game where we're trying to replace the lead in the structure, and we're moving across in the periodic table from the lead to try and get some sort of electronic doping. We're doing this a bit blind at this stage, and I'll show you what the result was. The nice thing, though, it's very easy to grow large crystals by this method, so it gives us good amounts of material to work with. We could see that the bismuth goes into the crystal, and it goes, we think, somewhere on the lattice. We don't see any other phases emerging. And we can put very large amounts in. We see a small change in the lattice parameter and a bit of disorder in the lattice when we do it, but they're quite small. So easy to synthesize and easy to get dopants in. And then we measure the thermal conductivity This is by the laser flash method that was introduced before. So this is the method that's typically used on bulk materials, because these are bulk materials. And we get a thermal conductivity of about 0.35 watts per meter Kelvin. So pretty much the same values you see for polymers. So great, we have a crystalline material which should have good mobility with polymer-like thermal conductivity. Pretty reasonable Seebeck coefficient as well. So minus 360 or so microvolts per Kelvin. This is when we pile in an absolute load of dopants. And we increase the electrical conductivity by 4 orders of magnitude when we dope. So this is all very happy story at the moment. But 4 orders of magnitude increase in thermal conductivity isn't enough. Okay, we only get to about 10 to the minus 4 Siemens per centimeter. The ZT is 10 to the minus 6. And the doping efficiency, therefore, is about 10 to the minus 5%. So you sort of put in 10 million bismuth atoms for one charge moving around. And this is really the challenge. Okay, there's a lot that's very promising about these materials, but the challenge, I think the primary challenge at the moment is working out how to dope them effectively, and I'll come back to that later in the talk. There are fundamental reasons why it's difficult. You can get ionic transport in these materials, so you get ionic compensation of defects, and the electronic structure is also quite tolerant to defects, which is effectively what dopants are. Okay, so we'll talk a bit about doping again in a moment, but what I want to talk about now, because quite a lot of this talk will focus on the thermal conductivity of the various materials, is why these materials exhibit low thermal conductivity, and some work we've done related to that. And here we moved to the case of methyl ammonium lead iodide, MAPI. This is the most commonly used material in the field of solar cells. So here we've got the lead iodide cage in the structure. You produce thin films by co-evaporation of 2 salt precursors onto our thermoelectric measurement chip. When we do that, we see, okay, we can do the XRD and see that we indeed have methylammonium lead iodide. There's a small amount of lead iodide content, so unreacted lead iodide. So you form the methylammonium lead iodide from the reaction between the 2 precursors. So there's residual lead iodide, but as the film gets thicker, when you grow them to 100 nanometers, that disappears. So the other thing we notice as a function of the thickness of the films is that the grain size is increasing. We can measure that by SEM or by Schroer analysis of the XRD patterns. And I'll talk about how we measure the thermal conductivity in a moment, but when we do measure the thermal conductivity of these thin films, we see that the thick films have the highest thermal conductivity, and it gradually decreases as we decrease the thickness of the film. So from about, looking at a funny angle now, crossing the numbers, I think it's from about 0.6 down to about 0.4 or 5 watts per meter Kelvin. So the thermal conductivity is going down with the thickness, which means it's also going down with the grain size and the lead iodide content. Although which is the cause is what we need to look at. And the values we're getting are very similar to the previous literature. So before I discuss this a bit more about what's going on in the material, I want to mention the thermal conductivity measurement method. So there was a bit of discussion about this and presentation of this morning. So I use what's called a pseudo steady state 3-omega method, which is a bit of a strange title for the method, because 3-omega is in its nature a transient method. I'll explain how it works. This diagram shows you how the conventional 3-omega method works. You have your thin metal strip, so this is a thin film heater that has to be in contact with your sample, which is either in contact with something you're measuring or maybe an interlayer between that sits between the heater and whatever you're measuring. And it can be typically, you'll find mostly on a substrate. As a bit of recall, you apply a current to this thin film heater, which will be at a frequency omega, and that causes heating, which will be at a frequency 2 omega, also with a DC component. And that means because you have a temperature coefficient of resistance, that means that resistance has a constant proportionality to the temperature. You end up with the temperature with frequency 2 ohmmeter, varying at frequency 2 ohmmeter with a DC component as well, and therefore the resistance. And then when you do the readouts of your voltage, which is the product of current and resistance, you therefore get a signal that has 1 ohmmeter and 3 ohmmeter components. And you use a lock-in amplifier to select the 3 ohmmeter components. When you do that, and I know this is a slightly different equation to the one you've seen already, but the system is also slightly different, works in a different geometry. You end up with a 3 ohmmeter voltage that is a function of many things, including this K down here, which is equal to geometrical factors and the thermal conductivity of the material you're testing. You also have resistances and currents that you know, and you also have a frequency-dependent component at the moment. So this is your operating frequency, along with your Tor, which is related to your heat capacity. You've got Ds, which is your thermal diffusivity. And if you do nothing more, you'd either need to use the techniques that were discussed this morning, or you'd need to know those values to extract the 3 ohmmeter, the thermal conductivity from the 3 ohmmeter voltage. However, what we can do is now bring the frequency of the measurement down. So we're still oscillating the temperature of our hot wire, but we're doing it in roughly a frequency of roughly a hertz. And this means that this term now becomes negligible. Okay, so and what does that mean? It effectively means that the system we're heating up is reaching steady state during the cycle of the temperature oscillation. That's why we call it pseudo-steady state. We still have a lock-in amplifier to detect the 3 ohmmeter voltage, but the system is thermally in steady state. This is what our measurement chips look like. So they're for measurements of whole of ZT. So we have 4 contacts here with red dots, and we have a film under test, which is this rectangular region in the middle. So this is a Van der Poel measurement of the electrical conductivity, so in plane, and it assumes the sample is isotropic in plane. We have this smaller rectangle is a membrane, which I'll show in cross-section in a moment. Along the middle of that is your heated wire. In the middle of that heated wire, you've got an electrical contact, and that's your hot side, and your cold side is on the substrate. And then your heat is dissipated from this heated wire along the middle, and it's dissipated on the board in the vertical direction, so away from that heated wire. And what about this membrane? Well, in this area where we have, so heated wire, this yellow bit here sits on the middle of a 100 nanometer thick silicon nitride membrane. And then on top of the wire, we have a passivation layer, which was discussed this morning after a question. So we have electrical isolation of our heater, which is quite good, actually, from our film under test. And then we put the film on top. The reason why we can get such good insulation, I think, is because we're putting the film on top of the insulation rather than the insulation on top of the film. So we don't make these chips ourselves, we buy them. So the heat is dissipated from this wire towards the substrate at the edges, which means that we're measuring the thermal conductivity in the plane of the film and in the direction that's perpendicular to that wire. Bit of a jump now, so I've talked about the method. We'll come back to more measurements using it. So, but one of the questions is, why is the thermal conductivity that we measured in methylammonium lead iodide so low? And so we went to a collaborator, Professor Ming Hu, who's now at the University of South Carolina, and he looked at the phonon density of states. And there are a few key points that come out. So methylammonium in the structure can move, it can rattle around, it's very free to move, but there are no propagating phonons that exist on the basis of the methylammonium cations. On the other hand, the lead iodide cage modes are responsible for transporting the heat. They have a group velocity greater than 0. Nonetheless, although they propagate the heat, the methyl ammonium modes, the motion of the methyl ammonium can actually scatter the modes that are on the lead iodide cage, and that's what brings down the thermal conductivity. What about, that's why it's low overall, but if we look back to the original data, it decreases with thickness. And this is not thin enough to be an effect of boundary scattering in the film. So what's going on here? Well, we need to bear in mind this is a polycrystalline film, so it's not a single crystal like the first data I showed you. So there are grain boundaries in the film. And what we wanted to do is see actually what is the magnitude of the thermal resistance at those grain boundaries. And so we went to this equation for the Kapitsa resistance, the thermal boundary resistance. This thermal boundary resistance is Rk in this formula. You've got your intrinsic thermal conductivity of the material under test. You've got the characteristic grain size or domain size, and then that's your measured thermal conductivity on the left. Rearrange that, and you can see if you plot your 1 over your measured thermal conductivity against 1 over the dimension of the grain, you can extract, hopefully, the thermal boundary resistance and the intrinsic thermal conductivity, which is what we've done, with some reasonable error bars. Okay, so we find our intrinsic thermal conductivity, of course, is slightly larger, so about closer to 0.7 watts per meter Kelvin at room temperature. We see a Kapitsa resistance that's in the right range for what is reported for most materials, so around about 10 to the minus 8 meters squared Kelvin per watt. What's a little strange is that it increases as you go up in temperature. It's quite low down here, it's 150, 60 Kelvin, but has increased by a factor of 3 or 4 by the time you get to room temperature. We don't have a complete answer to that. What we did notice is that the lead iodide cages have phonon modes that are around less than 4 terahertz. They're plotted down at the bottom here in yellow and blue. The methyl ammonium modes have frequencies that are slightly higher. And so at about 180 Kelvin or so, we'd have expected all of the lead iodide modes to have been excited already. And then the methyl ammonium modes start kicking in after that. So we're sort of hypothesizing that something to do with the methyl ammonium is happening at grain boundaries that's maybe causing that increase in Kapitsa resistance, but I'd say it's a little bit uncertain. I've got correlation rather than solid evidence there. We also explored different morphologies for the same materials. This is methyl ammonium lead iodide again, but deposited by aerol-assisted CVD. So this is being developed at Queen Mary's and at Imperial for kind of producing halide perovskite solar cells in a more scalable way. And essentially they carry the precursor lead iodide as an aerosol deposited on the film and then react it with the methyl ammonium iodide. And this allows you to go to much bigger film thicknesses as well as doing batch processing at wafer scale. Of course, we checked that we got methyl ammonium lead iodide on the substrate. It's not got such a preferred orientation this time, so you've got grains pointing in different directions and a small amount of lead iodide. And this is the thermal conductivity. We notice 2 particular things here. One, the thermal conductivity is exceptionally low. We're now below 0.2 watts per meter Kelvin, and at room temperature closer to 0.1 watt per meter Kelvin. And we also see a discontinuity in the thermal conductivity at the phase transition. We wanted to understand both of those things. So why the low thermal conductivity? This has a relatively straightforward explanation, but I think it's an important one for you guys to be aware of. And this is that these AACVD films are rough. I should mention, by the way, that the people working on this have now improved the methods and they can get quite smooth films. They can do it very well now, but at this time, the films were very rough. What does this mean for measuring the in-plane thermal conductivity? Well, we're going to measure a certain thickness of the film, but actually the heat transport is going to have to go through various constrictions in the film. Okay, so every micron or so, there's a dip here. And that is really restricting the thermal transport, and they're really quite severe. They are, they are 10% of the peak thickness at these points. These are bottlenecks for thermal transport. And that's something I want to talk about again at the end in a different scenario. But please be aware of this if you measure very low thermal conductivities. And this is not specific to this technique as well. I think this applies to all thin film in-plane thermal conductivity measurements. The other one was what happens at the phase transition. Well, for this, we went back to the density, the first principles calculations. We told us, well, there's not a change in heat capacity across the phase transition. On the other hand, there is a collapse in the phonon group velocity along one axis of the crystal, along the C-axis. And that seems to be driving it. We don't see it in the evaporated thin films because the orientation of the crystallites is not such that this one is aligned in plane. So in fact, the C-axis is pointing out of plane, so we don't measure the thermal transport along that direction. But in the mixed orientation film from the AACVD, we do see the effect of this collapse in phonon group velocity. So good, so our data wasn't so crazy, we can explain it. But I think the key messages are, yes, these halide perovskites have exceptionally low thermal conductivity in bulk, but we can use nanostructuring to reduce that even further. If we use nanostructuring on the scale of about 5 to 100 nanometers, and the thermal conductivity is highly dependent on the deposition method. But ZT so far is very low. So the next thing we did was move on to this halide perovskite cesium tin iodide. This is now all inorganic, so sorry it doesn't quite fit into the hybrid nature of the story, but it's still, many of the other properties still feel like hybrid properties between organics and inorganics. So this time it's the cesium ion that's moving around in this cage here. And again, we deposit by vapor deposition from the precursors cesium iodide and tin iodide and use 3 different techniques. So one, we co-evaporate the precursors, they react on the surface together. Another, we put one layer down first and then the other sequentially, and then bake them afterwards to make the perovskite. And then we do this hybrid method where we do a co-evaporated seed layer plus a bit of sequential deposition afterwards to get a kind of mixture of the 2 of these. And that turned out to be particularly useful. So if you look at the SEM images, they have slightly different morphologies on the surface, maybe slightly different grain sizes, but not drastically. On the other hand, they do have quite different preferential orientations on the surface. If you look at the electrical conductivity of these, one thing we notice is it's extremely dependent on the exposure time to air. So the electrical this is well known already, the electrical conductivity in this system is coming from the oxidation of tin 2+ in the film to tin 4+. And this enables the release of the charge to actually dope the material. So if you leave these in air for a long time, you see the electrical conductivity increasing. So in the case of the co-evaporated film, that happens as for a perovskite very slowly. Okay, it's over the period of an hour, it reaches a peak. In the other 2 cases, it goes up very sharply and then starts degrading after that point. On the other hand, the maximum electrical conductivity reached is much higher, 30 or so Siemens per centimeter in this case, and it can be higher. So what's going on? Well, if you see an increase and a decrease, it's probably a competition between 2 different factors. In electrical conductivity, you've got the number of charges you're generating and the mobility of those charges. The product of those gives you the electrical conductivity. Indeed, if we do Hall measurements on a patterned piece of this material, you see the number of charges constantly increasing as you expose the material to air. That's the black curve. On the other hand, the mobility decreasing, the rate of decrease, it accelerates as you expose them to air. So we've got increasing charge carrier concentration, decreasing mobility. So there's an optimum air exposure to get the highest electrical conductivity in this material. It's not ideal, but it gives us something to play with. We wanted to improve the stability though, and so for information, we put a bit of tin chloride on top to try and go for a mixed halide approach that is known to increase the stability of the materials. Once it's on top, we bake it to try and get the chloride to incorporate into the perovskite structure, which it does, although we do see sort of tin chloride domains on the surface, so it doesn't mix entirely with the iodide. And it only stays near the surface, so it's only in the top few nanometers we find, which is also where we find the tin oxidation occurring. Does it affect the stability? Yes. Okay, so the key plot is the bottom right-hand side here. So we're just following the absorption at a particular wavelength, and we see that this one up here, which is the 5% tin chloride doped case, is significantly more stable in air than the others, optically. Okay, so now the thermoelectric part. So in the electrical conductivity, of course, these are temperature-dependent measurements, and we've got a different curve for each air exposure time in minutes, so 0, 3, 6, 9, 12 minutes, not very long, but enough to do some experiments on. So for short oxidation times, we see the electrical conductivity increase, and then for longer times it goes down, as we discussed. But for all oxidation times, we see the Seebeck coefficients decreasing. Okay, so that's the sign that we are doping the materials. The thermal conductivity is interesting, so we get to about 100 Siemens per centimeter. So at this electrical conductivity, we can see an electrical component to the thermal conductivity. So our total thermal conductivity is, of course, the sum of the lattice component and the electronic component, which is given by the Wiedemann-Franz law, so it's proportional to the electrical conductivity, the Lorentz number, and the temperature. And so if we fit our data, we find that the lattice thermal conductivity is about 0.38 watts per meter Kelvin, still very low. And the Lorentz number is this, and that's very close to the Sommerfeld's value of the Lorentz number, which is the value you get for a free electron model, and is typically, in most of the sort of ceramic thermoelectric materials, you get that value or maybe very slightly less. This is, I think it was reassuring that our thermal measurements, our thermal conductivity measurements, were sensitive enough to pick that number out. Okay, so when we do this, we get to a ZT of 0.14. Okay, very oxidation dependent, of course, and it's a dual optimization of the oxidation time and the chlorine doping, it turns out, as well. So that's a little bit more promising. I won't summarize that anymore, but there's some promise here, but we still have problems with stability, of course, being halide perovskite materials, but also with finding other systems where we can effectively dope them. We're continuing this, we're looking at stability studies, so one is to change the deposition order between cesium iodide and tin iodide. It turns out that has a huge effect on the stability. And another is to substitute some of the tin with germanium, and that has a different mass, different bonding, and what you then hope is that then gives you some phonon scattering. And it does, it brings down the thermal conductivity by another 25% to slightly less than 0.3 watts per meter Kelvin. And so we're still working on that. Okay. So now I want to switch from those sort of hybrid and not so hybrid materials to polymers, and specifically P3HT. And the first thing I want to look at is stuff that's been done in Strasbourg, so one node of this ITM. And this is the aligning of polymers for thermoelectrics. So they do this by mechanical rubbing of polymers using a system, that very specially designed system they have in Strasbourg, and then doping them to make them electrically conductive. In this case, they used P3HT, then doped with F4TCNQ. The great thing about this is you can get near total chain alignment. That results in very high power factors. This is the number that we have for this particular system, but actually the power factor enhancement in other systems since has been shown to be much larger. The question remains, what about thermal conductivity? So high power factor is great, and for some applications, high power factor is enough. But in other applications, we want to have high ZT. So we can see here, yeah, we've got the enhancements in the power factor, and I think I've already said that. So how do we do this? So these films can't be deposited on our measurement chips and then rubbed, because we deposit on a 100 nanometer thick silicon nitride membrane. It's just on a break. So they are, instead, we use a PSS sacrificial layer, deposit the P3HT on top, and then the mechanical rubbing is done after that. What does that enable us to do? Well, if we dip that in water, the PSS layer dissolves, and the rubbed film floats to the surface of the water. And then we can go fishing. And we just put our test chip in the water and try and land the film that's floated off onto our test chips. The nice thing about that is we can land the film with the polymer alignment either parallel or perpendicular to our heating strip. So parallel or perpendicular to the heat flow in our thermal measurements. And this will enable us to make asymmetric thermal conductivity measurements. But first of all, as a sanity check, this is just measurements of the unrubbed P3HT and not even doped. And we get the thermal conductivity of about 0.3 watts per meter Kelvin with an error bar. P3HT is typically 0.3 or a little bit below 0.3 watts per meter Kelvin. It's isotropic, of course, and it has an edge-on morphology. When these are rubbed, not yet doped, just rubbed, we see parallel to the direction of rubbing. You see the very structured P3HT absorption signature, but perpendicular, you see something more characteristic of amorphous P3HT. So this is very well aligned. Also, there's less absorption in that direction. So we get much higher degree of order after rubbing. And also, it switches from an edge-on to a face-on morphology, which is actually quite important for the thermal interpretation of the thermal conductivity measurements afterwards. The spacings in the crystals don't really change at this point. So what about the thermal conductivity? Well, now we have a significantly higher thermal conductivity along the chain-aligned direction, so about 0.6 watts per meter Kelvin. If we measure in the other direction, it's only 0.2 watts per meter Kelvin, so still very similar, slightly lower than our previous value, but still within error bars similar to what you'd expect with P3HT. So we can see a clear effect of the alignment in the thermal conductivity. What else changes? When we think about what else would depend on the alignment to change, we decided to look at the stiffness of these films. This was done by nanomechanical analysis, so using an AFM tip. And we found that the modulus, Young's modulus of an unrubbed film was around about 1.36 gigapascals. Rub the film, and it becomes a little bit more complex. You still see something around 1.3 gigapascals, but also components at much higher stiffnesses. Now, this is partly a topographical artifact. So where you have dips in the film, it's quite thin. You can feel the substrates underneath. The tip feels the substrate underneath, which is harder. It's glass. So it's partly related to the topography, but I'll show as well in a moment that that's not the whole story. Okay, let's dope the films now. So when you dope them, not much happens in the direction perpendicular. So when the chains aren't aligned with the heat flux, so we still have a very low thermal conductivity. When the chains are aligned with the heat flux, we see now around about 0.7 watts per meter Kelvin. Now, this might be a small structural change, but we should point out also that this is also consistent with an electronic thermal conductivity using the conventional value for the Lorentz number. So we'd expect an increase of about 0.08 watts per meter Kelvin, which is within our error bounds what we do see. What else do we see? Well, from this structure, we see a decrease in the pi stacking. Okay, so this might also be having, I think actually, sorry, slight decrease, I think it is. Please get my numbers right now. There we go, 3.8. So it has decreased a bit, yeah. Yeah, decrease in the pi stacking and an increase in the interlamellar distance when doping. So you'd think that probably in the pi stacking direction, that might be favorable for thermal transport. In the interlamellar stacking direction, that may not favor transport. When we dope, we see the disappearance of the components of the material that has a Young's modulus of around about 1.3. When we dope it, that has gone. Okay, so it looks like we are increasing the stiffness of our film. The topography is very much the same. Sorry, in this case, as the undoped case. The film is getting stiffer as well, and that might be driving the higher thermal conductivity. The most surprising result for us was that when we put in a doped sample that hadn't had the mechanical rubbing, and we were expecting something perhaps that was closer to the neat P3HT. It turns out that that came out around about 1 watt per meter Kelvin, really rather large. And if the previous results didn't challenge the idea that polymers always have low thermal conductivity, this result, I think, should. There's a small anisotropy, which might be the effect of blade coating. There's a small anisotropy already in the films, but it is very minimal. And if you look at this, could this be an effect of an electronic component of the thermal conductivity? No, it can't. Okay, it's way too big for that. The electrical conductivity is lower in this case than the aligned polymers. So something else is driving that. The pi stacking is reduced again from the the undoped case, so there might be in that direction there's improved thermal transport. And we still have an edge-on morphology. And that might be quite important. So an edge-on morphology is generally better for charge transports, but in the case of a face-on for thermal transport, if we have the pi stacking, the thermal transport is improving on the pi stacking direction, which becomes closer, that's out of plane. So it isn't going to be picked up by an in-plane thermal conductivity measurements. That may be limiting the thermal conductivity that we see in the aligned films when we measure them. And also, we see in this case that as compared to the undoped case, we now have a much stiffer, in fact, compared to all other films, we have a much stiffer film. Okay, so this is now about 3.6 or so gigapascals Young's modulus. So this is something we'd associate with high thermal conductivity. Oh yes, I just wanted to point out, so in some classical sort of theories of thermal conductivity, the thermal conductivity is proportional to the heat capacity, the speed of sound in the material, and the phonon mean free path. The speed of sound is proportional to the square root of the bulk modulus of the material. So if you see an increase in modulus, you should see an increase in the speed of sound, and if everything else is the same, an increase in the thermal conductivity. On the other hand, it's to the power square root, so it's not a very strong relationship, and actually this alone can't account for the increase in thermal conductivity of our film. So maybe there's something like an increase in the phonon mean free path as well, which might be related to some more intimate aspects of the morphology. Anyway, I think the take-home messages are polymer chain alignment does increase thermal conductivity. Doping, in the case of P3HT, increases the thermal conductivity a lot. But it is a structural effect of the doping that can increase the thermal conductivity. And we can get thermal conductivities greater than 1 watt per meter Kelvin. The final message is, of course, we had high power factors. We still have a very good enhancement in ZT. It's just slightly less strong than the enhancement in power factor. So a factor of 25 enhancement in ZT between the aligned film and the unrubbed film. So I wanted to give another example of, well, P3HT. Okay, so this time the P3HT is drop cast, then we dope it with iron tosylate by immersion in a solution with iron tosylate, and then spin dry it. There's a different dopant and a slightly different dopant mechanism. Our motivation actually was to move to thicker films. Okay, so we wanted to move to micron thicknesses rather than 100 nanometer or less, which is what we looked at with the aligned films. And so we got films up to 3 or 4 microns, and when we dope, so there's a lot of data here. It's different spin-coated or drop-cast films with different concentrations. What we see is that they all reach a value of around about 1 to 200 Siemens per centimeter, but specifically the thicker ones, 170 Siemens per centimeter, which is really rather high for P3HT. And we can measure the Seebeck coefficients as well and get a reasonable power factor. That's not what I want to focus on, although it's a reasonably nice result. I think one interesting thing that came out of this was the thermal conductivity. And again, so what we're looking at here is the thermal conductivity as a function of the concentration of the dopant in the solution we immerse it in. So basically, as a function of doping. And if you look at the black curve here, we see there's a very sharp increase in thermal conductivity at very low doping concentrations. And at this doping concentration, the electrical conductivity is still very low. So this cannot be an electronic contribution. If it was an electronic contribution, you'd get what is the red curve, okay? And aside from the ZT there, which reaches quite a good value for P3HT on thick films, so it's 0.08, so near, more or less 0.1. So I've missed a 0, haven't I? 0.008, more or less 0.01 for P3HT. If we look at the structural changes upon doping, and then without wanting to go into too much detail, we've got the change in lattice parameters on the right-hand side, and we got both the pi-pi stacking and the interlamellar stacking. We see that the lattice parameter also changes in the structure at very low doping levels, which is very much consistent with the change in the thermal conductivity, but not so well aligned with the change in electrical conductivity. So it seems that it's this structural change that is driving the increase in thermal conductivity, lattice thermal conductivity in P3HT at low doping concentrations. And I think that's an important message to leave with the polymers, which is that thermal conductivity isn't constant, and small amounts of doping can increase it quite a lot. And if I still got time, I'm not. Okay, I've been going a lot faster than I thought. So actually I want to now answer at least partly another question that came from the talk this morning, which is, what if your thin film has topography? Will you measure the intrinsic thermal conductivity of the material you're testing, or something else? And this came from a result we got. I mean, we've done a lot of measurements now, which I'm very happy with. So a kesterite thin film here, thermal conductivity 0.5 watts per meter Kelvin. Some metal oxides, tin oxides, zinc oxides. These values corresponds with what you'll find in the literature for these materials. So I was again very happy with our system. Monolayer graphene, I was particularly proud of this. So this is CVD graphene, so we don't get the thousands of watts per meter Kelvin, but get a value that's consistent with what's in the literature for CVD graphene, 300 watts per meter Kelvin or so. This polymer BBL, which comes from a node in this collaboration, has a high thermal conductivity, but that's understood. This results bugged me. So I was working with a group in Swansea on thermally deposited tin selenide, and we made a low power thermoelectric generator and showed we could get a nice material by this method. But the thermal conductivity was an outlier if we compare with other work in bulk by spark plasma sintering, melt annealing, single crystals, and so on. We were way below at 0.1, sometimes even below 0.1 watt per meter Kelvin. And so I told my students to go and look at this sample in more detail to find out what's going on. And when we put it in the SEM, we saw this. Okay, so we saw that the film was made up of these sort of thin sheets of tin selenide pointing up off the surface. And they form a very porous structure. But if you think about thermal conductivity in plane, it looks like a network structure with holes in it. So it's not a complex network of thermal transport pathways, equally, actually, as a complex network of electronic transport pathways, which will explain why our electronic transport was also quite low compared with the literature. So, what's happening to phonons inside these sheets? Well, if you look in the literature, we found that the reported phonon mean free path in tin selenide is around about 5 nanometers. The thickness of the sheets is around about 75 or so nanometers. So within a sheet, the heat's still moving in a diffusive way. So boundary scattering on the sheets shouldn't be a big issue. Or put another way, the thermal conductivity of the intra-sheet should be roughly the same as the bulk material intrinsic. So I wanted to look at this, to model this effects of morphology. So this morphology is based on some patterned polymer films we're testing at the moment. It's not directly related to the tin selenide, but is to show a point. And so we went to COMSOL multiphysics. This is a finite element modeling software, and models our measurement system. So at the bottom here, we have the membrane. This is the 100 nanometer thick silicon nitride membrane that we support our films on. On top of that, we have the film under test. So it's an organic, so it typically have lower thermal conductivity, say 0.4 watts per meter Kelvin. We set the left-hand side of this simulation to be the hot side, the other side to be the cold side, and we measure the thermal, the heat transport from one side to the other, so the heat flux through this structure, as a function of an indentation that we put in the middle. So basically making a thermal constriction in our system to see how our measurement responds to that topography. So you can look at this in different ways. On the left, we've got the system when you have no indentation. Okay, so we got, this isn't really 0 Kelvin, so it's just a fixed temperature and then 1 degree hotter on this side. And you see that the temperature varies. If you look at it, analyze the data, it's linearly from one side to the other. It's also, of course, the same in the membrane as it is in the material because they're in thermal contact. If you put an indentation here, it looks fairly similar, but you can see there's some slight distortion to this temperature map around the indentation. Now, if we look at the heat flux, the blue area is low heat flux. We have low heat flux in our polymer film. Of course, it's low thermal conductivity. We have high heat flux in our membrane, which has thermal conductivity of 2.6 watts per meter Kelvin. Put a defect in there, and you start to see little changes. You get high heat flux around the corners of the defects and low heat flux up in the corners at the top. And when you make a very extreme indentation, you can even affect the heat flux through the membrane. So the membrane here is accommodating heat flux from the polymer film that can't get through that constriction. So it's obviously a slightly different situation to a fully suspended film where that constriction might be even more severe on the thermal property measurements. So what I've plotted here is the difference in our measured thermal conductivity from the intrinsic thermal conductivity of our polymer. And this is just done in percent. And my student presented this to me and says, look, when we put this constriction, when we make it deeper and deeper, we measure, we can get up to 40% deviation in the measured value for polymer films and up to 100% for metal films. And I thought, oh no, right? We've been working with this for a long time. And this would be disastrous if we were having errors this big. So it's time to have a little panic. But once panicked, you should look at the data in more detail. The student took a very negative, very pessimistic view of how deep this indentation should go. So 100% indentation is a full break in the film. If we look at what we might actually have on the chip, if we spin coat a polymer film, single component polymer will be very flat. So we may only expect deviations of less than 10% in the thickness. And we get very small differences from the intrinsic thermal conductivity, which is why we can actually measure it. Drop cast polymers, maybe a bit more. Metal films, if we evaporate some of them, we tested some of them, yes, it should be in that range again. Polycrystalline films, it depends on the material, right? We saw a bad case with the methylammonium lead iodide, but probably most are in this kind of region. The thermally evaporated tin selenides is probably somewhere here. It's not exactly, I'm not modeled exactly the same morphology, so I can't be precise, but it seems, the indentations were definitely well over half of the thickness of the film. So that is why that one failed. That's why the methylammonium lead iodide gave a low value, and that's why I can trust our measurements on polymers and polycrystalline films. The key message from that is that the thermal conductivity of a film is a function of the intrinsic thermal conductivity of the material it's made of and the topography. Okay, maybe it seems fairly obvious put like that, but you need to bear that in mind. If you have thermal constrictions in your film, you will measure a lower thermal conductivity. You need to make sure it's not too much lower. Other things that came out of this modeling, which I'm not showing today, the depth of an indentation seems to matter more than its width. The reduction in thermal conductivity is proportional to the frequency of defects. The more we put in, so we put in a defect every 1.5 microns to match our experiment that we're still working on. If you make one every 1 micron, it will be more. Okay. However, I think the good news is that this effect is small for reasonable films, but you need to be alert in case you have very high topographies. I think that's it. Yes. Thank you.
Thank you very much. A very nice and comprehensive presentation. So, who's first?
Thanks very much for the talk. I had a question about the velocity, the speed of sound in the material side, because you focused mostly on how the stress-strain properties, or the Young's modulus, the dependence of that. But isn't there also a dependence on the change of density of the material upon doping?
There is, which I couldn't measure.
Okay, okay.
So, but we do know what's going on in the crystalline domains of the material, and I don't think that gives a significant volume change.
It does not give a...
Not to the crystalline regions. It might be a bit, but I think it's not so much. It contracts in one direction, it expands in another.
Okay.
I think the net effect is fairly neutral from the density perspective.
Okay, now I was curious because you are introducing the dopant molecules into the film as well, which changes the morphology entirely, and so the change in density might be...
I think it's safe to assume it's not exactly the same.
Ah, okay.
But whether it is a difference of a factor of 2, I very much doubt, but I haven't measured it.
Okay, okay, thanks.
Thank you for your presentation. For example, in these last results where you say that the thermal conductivity from samples with large defects in either the surface or topography, they deviate. That also, I'm assuming, accounts for maybe aggregates in the surface, or maybe, for example, small crystals from dopants in the surface, or...
Yeah, so you could go the other way. So
yeah, exactly.
You could, for example, I think I dumped the AFM images after my conclusion slide, but I've got AFM images of the of P3HT doped with F4TCNQ, and you see these crystallites on the surface.
Yeah, exactly.
They would have an effect of raising the thermal conductivity. I haven't modeled it to work out how much that would be. You know, I'd imagine much like the defect, if they are relatively small compared with the thickness of the film and relatively far apart, then that effect is going to be a few % or less. If they start to aggregate into, to start to look more like a film on the surface and take up a large percentage of the surface, then that is going to have an effect, yes.
Okay, thank you.
Thank you for the talk. It was very interesting. I have some questions regarding the first part of the presentation about the perovskites. So at a certain point, you showed the spectrum of the phonon spectrum, basically. How did you calculate? I guess it's calculated. I know there is some terahertz spectroscopy.
I got on the phone. No, I didn't do the calculation myself. So that was done by collaborators. I'm not going to risk, I think, trying to explain how they did it. Okay, I can maybe afterwards I can point you yeah, to the paper and some of the details, but
Sure.
I'm not an expert on that at all.
Okay, so and you
But
didn't.
it is first principles. Sorry, I should point that out. It is a first principles calculation. So it's a calculation of the phonon modes in a defined cell of the material, crystalline material.
Yep. And you didn't explore what the effect of doping with bismuth on the density of states. You didn't see anything?
No, because you mean trying to feed that into the modeling? Is that what you mean?
Yeah, because from what I understood, you started with the doping of the perovskite, and then you showed.
So what we don't have the information on experimentally is exactly what happens to that dopant in the material. Okay, so does it simply substitute for lead? Also, this isn't ion implantation as well. We're actually putting in bismuth iodide. Okay, so there's extra iodine lurking around, and actually that's quite a complex question. What we are doing with a slightly different material is going to the synchrotron with a different dopant on a different material to try and work out where it's sitting exactly in the lattice and what it's bonding to.
Okay, that's very cool. Also, I have another question regarding still perovskites and hot carriers in general, because they are, there's a lot of hype on the hot carrier solar cells in general.
Yep.
And usually there is this decoupling from the phononic part, and nobody really understands and can properly predict the phonon electron scattering mechanism, or even if the electronic transports really affects the vibronic density of states. So is it something that you are will go into? Do you have any ideas on the field, the topic?
You're thinking about thermoelectric effects in solar cells or just the thermal effects? I mean, I think there's thermoelectric effects, yes. I mean, the solar cells heat up. Yeah. Right? And some of these materials, they have quite large Seebeck coefficients when they're not doped, which they aren't, and they aren't doped in solar cells. So there are small voltages that could be developed if there was a temperature gradient within the solar cell.
Yeah,
okay.
my question
the question is if, and whether that can be sustained. It's low thermal conductivity, which would help, but also it's the thin film technology. So whether you really get
my questions were more about the hot carriers, not the temperature of the perovskite itself, and how if that affects actually because hot carriers, in perovskites are strangely long-lived, and nobody really knows how.
It's a question, therefore, of electron-phonon coupling.
Yeah, exactly.
I think, and I don't know the answer of how strong that is. Okay. Actually. Electron-phonon scattering, rather, yeah.
Thank you so much for the wonderful talk. So I have a question regarding that, the perovskite too, like regarding the you have shown a phononic band structure, and simultaneously you show a phononic contribution to the density of state. So my question is, it like it depends on the for different like which case space point you are looking to into the system. So it should give a different phononic density of state, which is like the different peaks for different case space that you're looking through, and also like the partial density of state, like which elements is contributing how much. It is also dependent on, I think, I don't know, but like it should be dependent on the case K point. So how do you decide which case space point you are considering for the phononic density of state calculation?
The one that's per elements. I think.
Yeah, in the starting slides, yeah, you have shown a phononic density of state.
Yeah,
so,
and then there was the contribution from each atom.
The partial density of state.
I think that's integrated over the modes. I think that's all of the modes.
For all of the modes, or for a part, because for different modes there is different band structure splitting in the state, and for different if you choose different case space points, so you will find different peaks in the phononic density of state, so different contribution.
Yeah.
I think the different contribution for the elements too. So it should depend on which case space point you are looking through into the system.
Well, yes, you could. Yeah, you should certainly separate it out further into element and case space point. But I think that plot which shows the elements, I think that is I'd have to
all
check.
The case space point, like
I think it is. Yeah, so it's done by energy, so it's looking at all the modes at a certain energy. But I could be very wrong. I'm not. I think I'm being quizzed on the modeling that I didn't do. I was mostly showing it to show the outcomes. But yeah, we can talk about that in a bit more detail.
Okay.
Yeah. Sorry, I can't give a full answer.
Anybody else? If I may comment something, maybe I'm wrong also as well, but probably you focus more on the modes we have the highest speed of sound, right? The modes which are flat, the dispersion is flat, basically speed. The group velocity is very slow. So the contribution to the thermal conductivity is relatively low. So actually you want modes with a large slope, which are the ones that probably will carry more heat. And this is the typical comparison that you make between the longitudinal acoustical and transversal ones. The transversal ones are flat when you go to the edge, and so they do not contribute as well as the LA modes. Yeah. This would be one of the ways.
That's definitely true.
Choosing if you want, or just trying to guess which ones are contributing in a higher extent. Nevertheless, all of them contribute. That is clear.
But that's precisely why the methyl ammonium shows up on that plot, because they do have a group velocity of 0.
Okay. One more question, yes, sir.
Thanks for the great talk. I have a quick question and a comment. The quick question is in the first part of your presentation, when you see the phase transition in MAPI, I think you were showing the phase transition from tetragonal or torrhombic, maybe.
Yep.
And at that, if I'm not wrong, at that phase transition, the methylammonium should lock. It should stop rotating. And that's the reason why people was claiming that the thermal conductivity was very low. That is the rattling atoms concept.
Yeah.
But here what you show is that very marginal change in the thermal conductivity associated to the locking of the methylammonium. So my question is whether, I mean, I know that this was the sample with a lot of boundaries, maybe it's dominated by boundaries and that's it. But my question is whether are we really interpreting correctly the fact that the thermal conductivity is low because of the rattling organic, if whenever you freeze the molecule, then there is almost no change in the thermal conductivity?
Yeah. So I think there's a couple aspects to this. There were two things that we noticed as a function of temperature. So one was the jump in thermal conductivity as you go down in temperature. And that seems, or I suppose the drop as you go up in temperature seems to be linked actually to the lead iodide modes on that cage. So there's a collapse in the phonon group velocity along one particular axis. In the thin films, the thinnest thin films, that axis points out of plane, so we don't pick it up. In the thicker film, there's a mixed orientation of crystallites, so we pick it up a little bit. Okay, that's what we believe is the reason for that change. So that's related to the lead iodide, related to the methyl ammonium. The methyl ammonium, what I was looking at was the Kapitsa resistance, the thermal boundary resistance, which seems to start to increase at that point where the methyl ammonium modes start to get excited. But that's only related to boundary resistance. It's not, of course, that's not related to the bulk property, the bulk thermal conductivity of a crystallite. So within the crystallites, that's not being probed by the thermal boundary resistance. That's only probing what's happening at the edge. So I don't know what's happening at the edge. There's a lot of stuff happening at the edge, but that change in the thermal boundary resistance just seems to be at about the right temperature for the methyl ammonium to be doing something, as you say. Below that temperature, it's not really moving. Above that temperature, it's starting to move. But I can't pin it down 100%.
Thanks. Well, just a comment, if I may. We heard a talk this morning about how doping decreases the thermal conductivity. So I think there is something there to be studied in detail. What is the effect of dopants on the lattice thermal conductivity? Because it may be in this.
Yeah, I mean, I think that's
interesting difference between the two, going in the opposite direction.
That's the conventional wisdom. Defects generally bring it down, but dopants change the morphology so much in organic systems that it could do anything.
Okay, I would suggest we thank the speaker again, please.